Welcome to Math 106, Chapter 4.1 and 4.2, where we're going to learn about exponential functions and then how to derive them. So exponential functions have the form f of x is equal to b to the x. Another variation of this can be y is equal to a times b to the x, where a is going to be some multiplier. We'll learn what that does for us. But ultimately, b is considered your base. This is going to be some sort of numerical value. And x is your exponent now. So your variable is now in your exponent. Typically, we see your base as your as your variable raised to some sort of power, but now it's going to be reversed. So your variable is the exponent. Now recall what we've done from your chapter 0 section where we first learned about the laws of exponents. So let's see if you can take care of these first few quick examples. So pause the video if you need to. These laws of exponents are over here just for like a real quick refresher. So pause the video, see what you come up with those four. So first off, keep in mind with these quick examples, if we have a division sign and we have x above and below, we can subtract these two x value exponents. So notice that here it's going to be top heavy, right? 6 is bigger than 4. So we're going to leave lots more x's up on the top. So we can say, okay, 4, we're going to subtract 4 up above. So you'll leave behind two x values, and this being a positive 2 can remain, but we still have the 3 that is left over on the bottom. That is from your coefficient, 1/3. You can also write this out as well as just having 6 x's above and 4 below. You have the 3 there, and you can cancel out 1 for 1. And you'll notice that you'll have 2 left over. That is significant to that 2 there. Now for this one, right, we can go ahead and distribute. Because it's a monomial, notice that there's no addition or subtraction sign within your parentheses. We have just this duplicate amount. So if you wanted to, we could certainly write this out. The long ways, however many you have is however many you write. So I'll show that down here. But either way, right, the shortcut to this, instead of writing them all out, is to evenly distribute your exponent throughout your term. So we have really 5 squared, a squared, and b squared. 5 squared turns into 25. Then we have a squared and b squared. Again, the shortcut version of that is to multiply 5 times 5 makes 25. A times a makes a squared, and b times b makes b squared. Now, next up, you'll notice that we're finally seeing a negative exponent, in which case, if we have a negative exponent, we're going to drop it down into the denominator. Notice that it's only the one with the negative exponent that's going to change its location. So we have 3x, and now it's a positive 4. Then you still have y cubed right next to it. That has not changed. Notice that it has a positive exponent, so that one gets to keep its position. It's kind of stuck. Above in its place, we'll just have our placeholder of 1. Now we get to evenly distribute your exponent in, or you can write this out 4 times, which is going to be a lot of times, right? 3 times 3, that's 9, times 3 times 3, that's 9. So that makes 81. Otherwise, we can just recall that we have 3 to the 4th power, which is equal to 81. So you have 1 over 81, and we have x to the 4th and y cubed. And again, you can quickly see how many x's you have, in which case we have 4 x's. All right, now let's take a look. So first thing you might want to encounter is how to take care of this negative exponent. Again, you can, if you want to, distribute in your negative exponents, but lots of students who take this method end up, one, forgetting that it's a negative exponent. They kind of just turn it positive. But B, they don't always distribute it evenly. So just be aware of that, especially to your numerical coefficient. So instead, I say just drop it right down. So we have 3x squared yz to the fourth. Now that's to a positive 2, and in its place in your numerator, we'll just have a placeholder of 1. On your other term, there's nothing else to really simplify other than anything to the 0 power is going to be 1. You have none of these z's, therefore placeholder of 1. And that's anything to the 0 power. It's not equal to 0. So up here we have 9x cubed y to the fourth. Now we can still show that there's this multiplication sign in between that implied. So let's go ahead and bring these two ideas together. Or if you'd like, we can distribute evenly throughout. And notice that by distributing evenly throughout, or if you want to write out this twice, that's perfectly fine, is that when it comes to your exponents, right, what we end up doing to your exponents is instead of adding up the total amount of exponents, you actually get to multiply them. That is just if we were to write it out twice, right? But here in this form, we can add them really quick. Okay, so we have 8 z's here. Or if we want to keep it in this form, we can do 4 times 2, and that can equal to 8. So z to the 8th here. Y squared, x to the fourth, and we have 9. Now we can go ahead and clean it up. Let's see, those are going to cancel. We'll leave one of those behind. That's going to cancel and leave behind a 2, and the z to the 8th is kind of just stuck. So these should all be really quick reminders of what we've done in the past. So this is not new. Now let's take a look and use the properties of exponents to write the following expression in the form of 2k to the x. So in other words, we're going to use a base of 2 and now raise it to some k exponent being multiplied to your x. So k is the coefficient of x. Now what that might look like to start is, notice that 4 needs to now, because that's your base here, notice that your exponent is up here with your variable, but we want to transform this 4 into a base of 2. So we can ask yourself the question, okay, 2 to the what power is equal to 4? Well, 2 squared is equal to 4. So this 4 becomes a 2 squared, I should say. So 2 squared. This 4 becomes a 2 squared. And then we keep the exponent here, right? That kind of just drops down. And now to clean it up, to get into the form, right now we want 2k to the x. Right now we just got that base of 2. And now we have to clean it up to make it a little bit better with your k value. So you'll notice that when you distribute that in, you're really going to be multiplying here. So really have 2, or 2 to the 2 over 1 times 5 over 2x. Now these can cancel, so you're left with 5x. So we have 2 as your base, and then 5x as your exponent. Now let's see if you can try that again here. You'll notice that everything is already in the base of 2, so less work for you. You have the product property where we are multiplying 2 of the same bases. So see if you can clean this up to start. We can combine your exponents by addition. In this case, it's going to look like subtraction because your x value is negative. I'm so sorry, you're going to hear a little bit of background noise. So you have 2 to the 3x to the 1/2. And now you can combine your 3 times your 1/2 to be 2 to the 2/3 x. All right, let's try it again. We cannot use the product property quite yet. We instead, just like we did for your first view, can we write these two to have a base of 2. So we'll show that these have a base of 2. We'll put your exponent on the outside. So 2 to the what power can get you to 8? Well, that would be 2 to the 3rd power to be 8. And 2 to the 4th power will be 16. Now let's clean these up. We have 2 to the x because these two are going to cancel. And again, these two will cancel when we go to multiply it in. So you have 2 to the x times 2 to the 3x. And now we can go ahead and use your product property. So 2 to the x. Now we can go ahead and add these two together to get 2 to the 4x. We're going to leave that last one alone. Instead, we're going to move right on to example 2, where it says, let f of x equal to 3 to the 5x. Determine all x for which f of x, that is this, is equal to 27. So when it says determine all x values, all that is really trying to say is to solve for x. And if we know that we have f of x here and f of x here, we can set them equal to one another. 27 is equal to 3 to the 5x. And the whole reason why we've been trying to match these bases, this one was kind of specific, hey, let's put it into a base of 2, but really you can do anything as long as you're trying to solve for x. Now, what this is called is solving exponential functions with elementary cases. So in order to get your exponent down, right, we cannot just divide by 3 to the 5th, right, because it is directly attached. This is going to be some sort of numerical value. So instead, let's try and match your bases. So let's try and match 27 to have a base of 3. So 3 to the what power is equal to 27? Well, 3 to the 3rd is equal to 27, which is equal to 3 to the 5x. So that can kind of just follow through. And now what's really nice about these elementary cases is that we can therefore ignore these 3's as your base, because now it's all about your exponent. Your base is matched, and now we need to come up with an x that matches. 3 is equal to 5x, and let me replace that 3 over here. So we can go ahead and divide 5. So you have 3/5 is equal to x. And there you have solved for your variable. Essentially what we've just done is that when the base matches, we can ignore the base. Now, typically you want to get them on either side, but keep in mind what we know from the past. If they're being multiplied together, you're still going to add or subtract your exponents, depending on if it's negative, that sort of thing, and so forth. So don't let all of those ideas kind of just go out on the wayside. Now, you could always check your answer as well. So check. If we know that x is equal to 3/5, and we know that we have 27 is equal to 3 to the 5x, and x is now 3 over 5, we can conclude that if we scratch out these two 5's, because we have one on top and the bottom, that we have 27 is equal to 3 to the 3rd. So 27 and 3 to the 3rd is 27. So you can always confirm by kind of just putting it back into your original equation and see, does it actually work? Now let's take a look at these exponential graphs. Now, what do you notice about your graphs of exponential functions? So we have a lot of different exponential functions. This one is in green over here, 1.1 to the x. We have this red one, 1.8 to the x. This blue one, y to the 5x. And then we have this purple one as 0.5x. So what are we noticing? Well, we should maybe notice that we have a horizontal asymptote. So your horizontal asymptote, that is a line where your graph cannot touch. So if we were to draw that dotted line, it should be showing up right around this x-axis here. Notice that your graph isn't crossing that line. This is where y is equal to 0. This is your horizontal asymptote. So exponential functions have horizontal asymptotes. They do move with your graph. If our graph is going to move up or down, our asymptote will also move up or down with us. Now, another thing to notice is because we have a horizontal asymptote, are we going to have an x-intercept? No, we'll have no x-intercept. More likely, in some variations we can, but usually this horizontal asymptote for your parent functions, as long as you haven't moved them up or down, is it's going to prevent your graph from touching your x-axis. So typically there are no x-intercepts. However, your y-intercept, we should all note that we have one, and that is hovering around 0, 1. Now that is the case forever and always, because what do you know about x is equal to 0 as your exponent here? If that turns to 0, that's 1. If that turns to 0, that's 1. If that turns to 0, that's 1. Anything to the 0 power is 1. Now again, your variations can change if you're adding and subtracting, moving your graph up and down, left or right. That does change slightly. Now, when it comes to your graphs, right, the green, the red, the blue, the purple, but let's talk about the purple in a moment, but focus on the green, red, and blue. And looking at your bases, what do you notice about your base? Well, as the base is increasing, right, our graph is going up a lot faster. So you could say something along the lines of, as the base increases, the function rises faster, right? And notice that something about your base, if we said, okay, let's take f of x is equal to 1 to the x. And let's say, okay, now evaluate when x is 0. Okay, 1 to the 0, well, that's equal to 1. Okay, let's do it again. 1 to the 1, that's 1. And again, 1 to the 2, okay, that's 1. To the 3rd, okay. So what's going to happen here? Well, 1 raised to anything is just itself. So noticing some of your bases, we have to exclude 1 as your base, right? So we have to exclude 1. Because it is going to turn to a constant function. So it'll flatten out and it'll be a line instead of a function itself, or an exponential function. There's also another one that we would have to exclude. So let's, in this case, take 0 to the x power, right? So if we said 0 to the first, well, that's 0, okay? 0 to the second, that's 0. And again, same idea. So exclude 0 and 1 as your base. So that just means that as we're going through with your x values, your bases are going to be between 0 and 1. Yeah, and you'll notice that I'm going to exclude your negatives because your negatives are actually going to be more of a transformation. So it's going to flip your graph over the x-axis or the y-axis, depending on where your negative is located. But your bases, the base, if it's between 0 and 1, or if it's greater than 1. So those that are greater than 1, we are going to be increasing. So these are going to be growth. Whereas if they're going to be in between 0 and 1, so notice like your purple one, instead of a growth, we're going to decay. So if it's any sort of base that is in between 0 and 1, we are falling. We have a decay. Now, those are really all of the important aspects of your graph that we will be talking about and really focusing on. And again, these are just one specific variation of them. Like we haven't seen where your exponent has really moved much. We haven't gone like left, right, center, that sort of thing, but we're going to start to see that eventually. So now let's move on to 4.2, where we kind of get exposed to the exponential function e to the x. So there is a particular value of a base b between 2 and 3, where the graph of y is equal to b to the x has a slope that is exactly equal to 1 at x is equal to 0. Therefore, right? So if so as we just covered, right, with your with this in mind, right, if your slope is exactly equal to 1 at your critical value and x is equal to 0, this is going to be when we have e to the x. Now, e to the x, again, this is just your base here. We call this your exponential function, where e is approximately, and if we were to put this into your calculator, if you typed in e, you'd come up with 2.71828 ... Some calculators will do it more, but if we were to round in a way, we would say this is about 2.72. We're going to treat this kind of like we did pi, where we know pi is, okay, 3.14 ... Some of us can reiterate a little bit more past your 2 decimal places, but notice that with pi, we typically use the pi symbol. As we go on your calculators, we're going to be using this e symbol rather than 3.14 or 2.72. These are just irrational numbers. These are very special numbers, though. Now, with the derivative of y equals b to the x, we have d over dx, right? The derivative of b to the x is m, your slope of b to the x, where m is the derivative, right? Your slope, d over dx of b to the x when x is equal to 0. Now, in a very, very special case, and in these cases, if b is equal to 2, so if we have 2 to the x, your textbook, right, takes the time to show you, okay, this is where you derive. For me, we're not really going to be interested in it because we're going to be more interested in e. That pops up a little bit more for you guys. But m is about 0.693. And if b is equal to 3 to the x, m is roughly 1.1. And again, there's an exercise in your textbook that defines how we get these. We're not really going to use it. But for us, what we're interested in is that one special piece where we said, hey, this e to the x, right, its slope has exactly equal to 1. So if we know that your slope here is equal to 1 and it's your exponential function of e, if e is being used, that just means the derivative of e itself, right? E itself, that derivative, so that's your m piece from before, is equal to 1. Therefore, we're left with the derivative. So the derivative of e is just 1 times e to the x, or just e to the x. That is to say that the derivative of e itself is itself. The derivative of e to the x is equal to e to the x itself. Because m is equal to 1, so 1 e to the x is e to the x. So when it says write the expression in the form a e to the kx for some constant a and k, First, let's see if we can clean up what we have so far here, right? Using the properties, and we'll talk about your derivative a little bit more, but using your properties, right? We have your negative exponent. Well, using your properties, right? We can go ahead and distribute this in. So we have 3 squared e to the 2 times 2x times e to the x all over e to the negative 2x. So now we have 9 e to the 4x times e to the x over e to the negative 2x. So now we can go ahead and say this is 9 e to the 4x plus x, that is 5x, over e to the negative 2x. And now we can go ahead and add those two together. Well, we're going to subtract, right, them together, but it ends up being addition. 9e to the 7x. And this is in the form a to the e k x. Let's have you guys try it one more time over here. Well, let's raise it up first. We'll worry about your square root here in a second. So you have e to the x times e to the negative 7x. So this is now e to the negative 6x over here. And now let's go ahead and show that this is really e to the negative 6x times your 1/2, right? This transforms into 1/2. So really this is e to the negative 3x, which is equal to 1 over e to the negative 3x. So your a here, right, if it's a e to the kx. Well, I guess if you wanted to keep it into this form, that would be fine. And that should be a positive. This is more likely what I'm looking for though, but I guess if we're asking for this specific form, that would be all right. So now let's go ahead and get some work with your derivative. I'm not sure why I put example 3 in there right after talking about the derivative, but nonetheless, let's go on. It says, find the tangent line to the graph of f of x is equal to e to the x when x is equal to 1. All that is saying, right, we have encountered these problems time and time again with these tangent line is first we need to derive. So step 1, we need to find the derivative. So f prime of x, we said, okay, if we have e to the x, that's really m e to the x, where m is equal to 1 in our case. So in other words, our derivative is just itself. So e to the x. Maybe I define that a little bit better. So you don't think I just intentionally wrote e to the x if you were to look back, right? That's your derivative. So now that you have your derivative, right? Your derivative, we want to know about slope. We want a tangent line. So we now need your slope. So find the slope when x is equal to 1. So f prime of 1, we have e to the first, and this is your slope. This is m. So m is e to the first power. So now step 3, right? We have y equals mx plus b, right? That is your typical format. M we know to be e to the first. X we know to be 1. So now we need to figure out y. We figure out y by plugging in your x value into your initial formula. So that would be e to the first. So we have the point 1 e to the first. You have your slope of e to the first, right? I know it's a lot of e's, right, to the first power, right? But 1 is your slope, the other is your point, And now we get to go ahead and plug it in. Now we're not going to be using E as 2.72-ish, right? We kind of act like we do with pi, so we just work it in. So if we have y equals mx plus b, we have y, which is e to the first, is equal to your slope, e to the first times 1 plus b. So when you move it over to the other side, b is equal to, so that is equal to 0. So step 5 is that we have y is equal to your slope, e of x, and then you could say plus 0. Let's have you guys try it again over here. Now, we're not interested in finding the tangent line. Instead, we are just working on your derivatives. Right now that we've carried over into chapter 4, right, we're bringing our knowledge from chapter 1, which we talked about, okay, how do we tackle these such problems? Chapter 2, we talked about graphing, right, ways to find your critical value, your inflection points, your extrema. Now in chapter 3, we talked about deriving, right? With the quotient rule, the chain rule, the product rule. So this is where chapter 3 comes into play. So if we are asked to derive, we can say one of them is f of x. We'll just say that is in your parentheses, 1 plus 2x. We could go ahead and derive. We also have g of x, that would be your other one. And we can go ahead and derive. And again, that's just your derivative of itself. Eventually, we'll talk about some chain rule. I believe that's going to come up in your next section. So we just have to kind of hang on to it, right? But the power rule just says that we'll take the derivative of the first times just your regular second times your first times the derivative of your second. So they're just taking turns to derive. So in our case, we have 2x times g of x plus your f of x times the derivative of g of x. Now, right, you're going to be asked to simplify. So can you highlight something that they have in common? Well, they have your e to the x in common. So let's go ahead and take that out. You're left with 2x plus 1 plus x squared. So let me arrange that. X squared plus 2x plus 1. Now let's go ahead and see if this is factorable. It is. So we have e to the x is equal to x plus 1, x plus 1. And because there's 2 of them, we can write that duplicate amount. So this is fully simplified. Let's have you guys try it again with your other ones to see if you can pause. So we have your quotient rule here. We have 1 plus e to the x, that's your top. The derivative of it is just itself, e to the x. Notice that your constant drops away as always. So your derivative is just your one that has the e to the x. G of x, we have 2x. G prime of x is just 2. So now we have to use your quotient rule. I had a former student, now he's moved on to another instructor, and he often comes into our math lab, and he told me that they have kind of their own saying where it says high d low minus low d high over low squared. What that is just saying is that you keep your first one, right? The top one, this is high, this is low, but you keep the first one the exact same. And then this one is the derivative of the lower of the two. And then you keep the lower of the two the same, and then you derive your second one. and then you keep the lower one squared. So if you like that, and it's a little bit easier to understand than the quotient rule that I typically write out, then there you have it. So either way, we have, let's see, high d low. So we have high as x plus e to x. Low, we have just the derivative because this is high and this is low. This is d high and this is d low. So we have 2 minus, and then we have 2x times 1 plus e to the x. Oops, I'm so sorry. I did not actually get to derive that one. This is just e to the x over here. All over 2x squared. So is there something that we can see that all three terms have in common? Well, even if we took this, right, and let's see, we should see that they do end up having a 2 in common, but let's do this part out. Right, if we distributed that bottom one in, we should have 4x squared. But you'll notice that we have an 2 in common for each of them. That'll leave behind a 2 here. So if I were to get rid of some things, that would be this thing here. An x squared, that's there, that's an x. And then you'll notice that you can drop this portion off because we no longer need that parentheses. So we have e to the x minus x e to the x plus 1 over x squared. And that would be your final answer. So again, you can do quotient, product, and chain rule with now your new derivative of e to the x. We're going to leave it there. We'll talk more about some other derivatives when it comes to these ones later down the road, but those aren't like super important. We're really just going to be honing in on E and ln.